Hello learners, myself Dr. Priyadarshini, Patna Women's College Autonomous. Today we are going to learn about transportation problem, which is a topic in the course Optimization Techniques of MCA program. The learning objective of today's class is to formulate a transportation problem and to locate a basic feasible solution of a transportation problem by various methods. In operations research, linear programming is one of the models in mathematical programming which is very broad and vast. Mathematical programming includes many more optimization models known as nonlinear programming, stochastic programming, integer programming, and dynamic programming. Each one of them is an efficient optimization technique to solve the problem with a specific structure, which depends on the assumptions made in the formulating the model. The transportation problem is a special kind of linear programming problem whose objective is to transport a homogeneous commodity from various organizing factories to different destinations or markets at a given total minimum cost. The model can be represented by the network in the given figure 1. There are m sources and n destinations, each represented by a node. The arcs represent the routes linking the sources and the destinations. Arc ij joining source I to destination j carries two pieces of information: the transportation cost per unit Cij and the amount shipped Xij. The amount of supply at source I is Ai and the amount of demand at destination j is Bj. The objective of the model is to minimize the total transportation cost while satisfying all the supply and demand restrictions. To understand the problem more clearly, let us take an example and discuss the rationale of transportation problem. Three factories A, B, and C manufactures sugar and are located in different regions. Factory A manufactures B1 tons of sugar per year and factory B manufactures B2 tons of sugar per year and C manufactures B3 tons of sugar. The sugar is required by four markets W, X, Y, and Z. The requirement of the four markets is as follows. Demand for sugar in markets W, X, Y, and Z is D1, D2, D3, and D4 tons respectively. The transportation cost of 1 ton of sugar from each factory to market is given in the matrix below. The objective is to transport sugar from factories to the markets at a minimum total transportation cost. The above problem here has got the following properties. Here we can see that it has an objective function, it has structural constraints, it has a non-negativity constraint. The relationship between the variables and the constants are linear. We know very well that these are the properties of a linear programming problem. Hence, the transportation problem is also a linear programming problem, but a special type of linear programming problem. What are the steps to solve a transportation problem? First, we try to find an initial basic feasible solution, and for that we need to balance the given problem. Balancing means check whether sum of availability constants equals to the sum of requirement constants. That is, summation Bi should be equal to summation j. Once they are equal, you go to step 2. If not, by opening a dummy row or dummy column, balance the problem. The cost coefficients of dummy cells are 0. If summation Bi is greater than summation Dj, then open a dummy column whose requirement constant is equal to summation Bi minus summation Dj and the cost coefficient of the cells are zeros. In case if summation Dj is greater than summation Bi, then open a dummy row whose availability constant will be equal to summation Dj minus summation Bi and the cost coefficient of the cells are 0. Once the balancing is over, then we go to step 2. In step 2, a basic feasible solution can be obtained by three methods. northwest corner method, least cost cell method, and Vogel's approximation method, generally known as VAM. After getting the basic feasible solution, give optimality test to check whether the solution is optimal or not. There are two methods of giving optimality test: stepping stone method and modified distribution method, which is known as Modi method. Now we see the properties of a basic feasible solution. When we have a basic feasible solution, we need to check its properties. Say the allocation made must satisfy the rim requirements, it must satisfy availability constraints and requirement constraints. Second, it should satisfy non-negativity constraint. Third, total number of allocations must be equal to m plus n minus 1, where m is the number of rows and n is the number of columns. Let us take one example. 4 factories A, B, C and D produce sugar, and the capacity of each factory is given below. Factory A produces 10 tons of sugar, B produces 8 tons of sugar, C produces 5 tons of sugar, and D produces 6 tons of sugar. The sugar has demand in 3 markets, X, Y and Z. The demand of market X is 7 tons, that of market Y is 12 tons, and the demand of market Z is 4 tons. The following matrix gives the transportation cost of 1 ton of sugar from each factory to the destinations. Find the optimal solution for least cost transportation cost. Here we can see that summation Bi is greater than summation Dj. Hence we have to open a dummy column whose requirement constant is 6, so that the total of availability will be equal of total of demand. In using the northwest corner method, first we need to balance the problem. That is, we have to see whether summation Bi is equal to summation Dj. If not, we have to open a dummy column or dummy row, as the case may be, and balance the problem. Now start from the left hand side top corner or cell and make allocations depending on the availability and requirement constraint. If the availability constraint is less than the requirement constraint, then for that cell make allocation in units which is equal to the availability constraint. In general, verify which is the smallest among the availability and requirement and allocate the smallest one to the cell under question. Then proceed allocating either sidewise or downward to satisfy the rim requirement. Continue this until all the allocations are over. Once all the allocations are over, that is both rim requirement, column and row availability and requirement constraints are satisfied, write allocations and calculate the cost of transportation. The count of allocation, if it is equal to m plus n minus 1, then the solution is basic feasible solution. The solution we got have 6 allocations, which is not equal to 4 plus 4 minus 1, that is 7. Hence the solution is not a basic feasible solution. Here we can see that the transportation cost is 101. Now let us see the same problem using the matrix minimum method or least cost method. In this method, the first step is to identify the lowest cost cell in the given matrix. In this particular example, it is equal to 0 because 4 cells of dummy column are having 0. When more than one cell has the same cost, then both the cells are competing for allocation. This situation in transportation problem is known as tie. To break the tie, select any one cell of your choice for allocation. Make allocations to this cell either to satisfy availability constraint or requirement constraint. Once one of these is satisfied, then mark crosses in all the cells in the row or column, whichever has completely allocated. Next, search for the lowest cost cell and proceed this way until all allocations are made. Then write allocations and find the cost of transportation. In the given problem, as the total number of allocations are 7, which is equal to 4 plus 4 minus 1 equals to 7, the solution is basic feasible solution. And here the transportation cost is equal to 70. The transportation cost using the northwest corner rule was rupees 101. This is all for today. In the next lecture, we'll continue with the third method of finding the initial basic feasible solution of a transportation problem, and its name is Vogel approximation method, also known as VAM. Out of the three methods, the VAM method gives the least transportation cost. Okay students, happy learning. Thank you for listening.